record. Okay, welcome everyone. In this week's QTFMS seminar, we host Luca Ciambelli from Perimeter Institute of Theoretical Physics. He is going to talk about Carrollian geometry, the language of Null Hypersurfaces. Luca, you may start if you're ready.
Okay, yes, I am. So let me start. First by thanking you very much, Omer, and everybody for being here, for organizing this. I have to confess that I didn't know about the seminar series that you're organizing. And so when I received the email, I was very pleased to discover this. I think this is an amazing initiative. And the fact that it started through an independent decision and not necessarily academic decision from top down, but from students that are eager to learn new topics and to be more connected to outside of Turkey science. I think that's incredible. It's a very good initiative. And so I just wanted to state my full support for whatever that means, but or whatever that can help. But I found it really, really very nice. So congratulations to you all for this. Okay, that said, I'm gonna start. I have 3 screens, but in principle, I'm sharing mine, and you should all be seeing my iPad. I gonna talk about a recent. Well, actually, I'm gonna talk about a review. So I'm gonna talk about Carrollian geometry and null physics, and I'm pointing you out to this very recent review I posted with my collaborator Putarak Jackson. There is a V2, and the V2 has some improvements that appeared last week, probably, or even, yeah, I think last week or beginning of this week. And so please, if you have the old version, the V1 that you saw a couple of weeks ago, download the new one because there are some improvements. I will not post. I want to set this up as a sort of a lecture, if you want, more of a, basic things, more of a, pedagogical introduction to the topic. So I will not talk necessarily about the latest developments, and therefore I will not cite all the amazing amount of beautiful works that has been done recently based on all these geometric structures. I really want to give you a general flavor of null geometry, the way we understand it from an intrinsic standpoint these days. And so I really redirect you to this review. There are some very few selected references in that review, but they on their hand contain a lot of references and applications. So you can use this as a lamppost to find the right literature. And if at the end you want to learn more about it, or you want to have some papers to read, please feel free to contact me or ask me directly. Okay? In the spirit of this being more of a pedagogical introduction to the topic, as I'm assuming that not all of you are necessarily familiar with all of this, I'm going to go slow. I have some slides, but I will not use slides. I will write down on the iPad so that the pace hopefully will be at the right pace for you to be able to follow. And also, I have set it up so that I can see all of you here. So, as I was saying, feel free to unmute yourself, to turn on your camera and ask any questions. I mean, I don't know how previously this has been set up, but I really enjoy it if it becomes more a dialogue and a discussion rather than just a front lecture. Okay? All right, let me start. I wrote a very quick overview, a very simplified overview or outline of what I'm going to talk about. So the first thing that I'll need to talk about is why null geometry. What is null geometry? Why it's hard if you think about it. I mean, this is just geometry, so you should think that Riemann, Ricci, Gauss, Levi Civita, and all these people already figure everything out. And to some extent, of course, it's true, but the modern formulation of this null geometric is very interesting, and so I'm going to go through that. And that is why I have a warm-up with a very simple example that makes you understand that, there's something going on here that is not so easy and familiar with. So just a very simple example to give you that feeling. And then I'm going to just do the top-down approach, so really define what I mean by null geometry. And the big chunk of this will be devoted to connections, because this is a topic that people are unfamiliar with. When people deal with null, they tend to I have the impression that to make a quick statement, sometimes two quick statements, really connections intrinsically on an geometry, something very subtle. And so to give you this up, and then to give you the more general framework to deal with it. And that will inevitably lead me to reading and to the point of embedding this null geometry into a bigger space. Will be anyway our most familiar application and interest of null physics as some null more technical results concerning curvatures, and hopefully the end point will be showing to you that Einstein equations projected on the null hypersurface can be very elegantly recast in terms of conservation laws of a stress tensor on the hypersurface. And that would be kind of the culmination that relates really to more recent applications. Okay, so essentially you should think of these first two sections as something fully intrinsic, and of this other two sections as something extrinsic, or better said, embedded. So in the first, except for the example I'm going to go through fast now, the other two sections will define what I mean by a null geometry without reference to an ambient space, as much as we can talk about a time-like or space-like hypersurface as a pseudo-Riemannian or Riemannian manifolds on their own. They don't need to be hypersurfaces of a bigger space. That's the logic I'm going to use in the first two sections. Okay, let me start. Warm up a sample, the easiest thing you could think of, which is Minkowski. You give yourself your Minkowski metric in your favorite coordinates. I'm going to use spherical coordinates. So I'll have something like this. D is my, so SD is the solid angle, it's the infinitesimal solid angle. So I'm going to use notation for which the manifold M will be D plus 2-dimensional. And the hypersurface that I'm going to call N, the null hypersurface, which then is going to be a manifold on its own, is D, plus 1-dimensional, of course. And the cuts of these null hypersurfaces are often called C. These are just where the solid angle live, and this guy is going to be D-dimensional. And hopefully, I have stick with this throughout the entirety of this lecture. So I hope I've been consistent. It's always D plus 2, D plus 1, D. Okay? And okay, so this is a D plus 2-dimensional manifold. This is Minkowski. So it's globally flat. We know it very well. And now let me sit on coordinates u equals ct plus r and v equals minus r and plus r. C is the speed of light, which I haven't set to 1. Customarily, we do so. And if you do that, of course, you can rewrite this metric simply as minus 2 du dv. And then plus, the radius is just v minus u square over 4. And then the solid angle. Okay, so this is just a bulk written in double null, right? You can think it in a 2D diagram as each point is a two-sphere, and from it you have a ingoing and outgoing null hypersurface departing, and that's your manifold M. And now I want to study hypersurfaces. You can study hypersurfaces at T equal constant. Those are space-like hypersurfaces. You can study hypersurfaces at R equal constant. Those are time-like. Or you can study hypersurfaces at U equal constant, for instance. So let me say my hypersurface, which I'm going to call N here, is defined at U equal constant. And for simplicity, I'll just take that constant to be 0. It doesn't matter. It can be any value, right? And now what is the induced metric? Well, it's very simple. You go in and you realize that the metric is just V squared over 4 times the SD2, where I'm pulling it back to the U equals 0 surface, right? No big deal here. However, you defined the hypersurface by selecting one coordinate to have a value. So this object is truly a D plus 1-dimensional manifold. And the coordinates on this manifold are V and the solid angles, coordinate theta, phi, etc., depending on the dimension. And so this is the first question. Where is V? V is here, but I don't have a dv square. So if I want to write it more in a more illuminating way, what you should really write is something like I have a 0 in front of dv square, and then I have another piece, which is the solid angle. This is really the line element on my hypersurface. There's nothing surprising going on. We know what is happening is that this hypersurface is null, and the nullity of the hypersurface means that there is no time component because the time component has a 0 in front of it. Okay, so nothing surprised on its own, but now geometrically this is kind of a cumbersome object to work with, because suppose that you want to take on that object the inverse metric that doesn't exist. This metric is obviously degenerate. If you write it down as QAB, so I'm gonna use indices. I'm gonna write the bulk indices as G mu nu dx mu dx nu. So in this case, x mu was u, v, and the solid angles. I just write SD formally, just mean theta, phi, etc. And then on the surface, I'm gonna add this is XA. Of course, u is no more a coordinate because it was a coordinate of the space, ambient space, but not of the surface. Oops. And this is v and the solid angles. And so if you write it like this, dxa, dxb, obviously the q is degenerate because the q as a matrix has 0, 0, 0, and then here there is the metric of the solid angle. Just I'm writing very sketchy right now. It's just an example to get you familiar with it. And so there's no inverse. And so we cannot write Christoffel symbols. We cannot write Levi-Civita connections. We cannot write curvatures in the usual sense. What does it mean to the parallel transport on this hypersurface? The many things that we're very familiar with pseudo-Riemannian geometry, are not available intrinsically on the null hypersurface because of this degeneracy. So what we say is that QAB is a degenerate, improperly people call this metric. Metric by construction is not degenerate. So what we really mean when we say that is a degenerate bilinear form, symmetric bilinear form, which is like the metric, but with some degeneracy, right? And even more cumbersome, if you think about that, is where the hell is time? I have a V here, but suppose now that you don't know where this surface comes from. And suppose I just tell you, I have a line element, which is this, times a parameter. Let me call the parameter lambda. How do you know that this is a null hypersurface or a null manifold better, or it's just a d-dimensional sphere? There's no way you can distinguish, right? If I just write this down, there can be a plus 0 times d lambda square or not. You don't know that, right? And this is a very easy and intuitive way to understand that giving just the degenerate metric on a null manifold is not enough. You don't have enough information to distinguish it from a perfectly non-degenerate d-dimensional surface. And so what is really important is you have also to supplement yourself a vector that in this case, that is going to be LA partial A, which in this very simple setup could be simply partial V. If you supplement a vector and the metric, degenerate metric, you have enough information to tell me that that's a null hypersurface. Why? Because you can simply compute what LA QAB is, and this is simply the vector. This is simply 0, 0, 0 is this guy here acting on a vector which is 1, 0. That's what dv is. And the answer is 0. Of course, right? It's that this 0 here is nothing but the 0 that we had up here in the degeneracy. And now that form enough elements, right? You give yourself a vector, you give your LA, you give yourself a metric, and you require LA QAB is 0. And notice, you require LA is nowhere 0. This was nowhere vanishing, right? It was not a vector that was multiplied by a function that was 0 somewhere. This condition really is telling you that Q itself as a bilinear form is degenerate. And those are enough information to determine what a null hypersurface, what a null manifold intrinsically is giving you a geometric structure on a null manifold. So you should think of LA and QAB as being exactly equal to GAB in a non-degenerate surface, is the metric information. So the geometric structure is more complicated. Okay? So this is a very simple setup, and just it already makes you understand. I'm gonna now move to the much more general. I'm just gonna start working in a coordinate-independent formalism with abstract indices, but I want you to appreciate how I see there is a hand up by Deepak. Give me just 1 second. I'll just finish this sentence and then you can unmute yourself. I just wanted to make you appreciate how already is different from pseudo-Riemannian geometries, and what we're gonna work on later might seem a bit abstract, but you can always have these very simple concrete examples in which you can check that what we're doing is just setting up the right geometric description. Yes, please. There was a question?
Yeah. Hi, Luca. You can hear me?
Hi. Yes.
So LA is a null vector with respect to the bulk metric?
Yeah, I mean, LA right now is null everywhere, right?
Okay. And so basically you have the null hypersurface and the normal to that hypersurface. These are the two pieces of data, right?
Exactly.
Okay.
Yeah, so what you're
Thanks.
pointing out, we're going to talk about it later with the rigging. What is truly
Okay,
happening?
sorry.
I'm going to explain. No, nothing to apologize. You're kidding. It's perfect cue in for the later sections. I'm going to explain it briefly now since you asked, but I'm going to come back to it later. What is, and I hope I'm pronouncing your name right, Deepak pointing out. What he's saying is that, this vector,
That's
sorry?
your pronunciation is actually perfect. So
Oh, perfect.
yes.
I'm glad it was an educated guess. Perfect.
Thank you.
Okay. So what is Deepak pointing out? Correctly so. From the point of view of the hypersurface, this L vector field, of course, is null. If you formally try to take its norm intrinsically on the surface and you define this to be its norm, of course, is zero. Right? No problem. But what is pointing out is that, okay, let's go into the bulk. And let's treat this object directly in the bulk. In the bulk, our metric was just 0, -1, -1, 0, 0, 0, dsd2. Again, I use this formal way to write the angle 1. I hope this notation is clear. And then he's asking, let's consider the vector field L partial V and check what it is in the bulk. Well, that's easy because the one form dual to that, I'm going to put now an arrow, the one form dual to that is just equal to minus du. So this is obviously null, right, in the bulk as well. But what is this null form? This null form is actually the normal one form to the hypersurface itself. Remember, the hypersurface was at u equal u0, and so the one form normal to the surface is d of u minus u0. This is what you can call n, typically, as the normal, and we're going to use exactly this notation. So it's true, when you have a bulk, the bulk provides for you both L and Q on the surface. And this is already the complication I was mentioning to you before. The intrinsic prescription, on the other hand, the intrinsic description, if you don't know a bulk, requires you to introduce Q and L as separate quantities. Okay?
Hello, may I ask a question?
Absolutely.
Can you hear me?
Please. Yes.
So my question is, we started by somehow finding a null metric, but can we also start from some type of a Newman-Penrose type of a classification, and so that we have a null subspace and a complexified sphere, and then we classify the how we classify the spacetime, at least for the black hole spacetime and such, and then take the null limit in a way that one of the null vectors are now gone and we only have L. We could also say not U as not zero, but we can identify some other vector M, let's say, and then take it zero after we find the inverse of it and everything of it. And is that a logical step, or
It's what you're describing is perfectly fine. From the perspective of the bulk, what you're describing is perfectly fine. Again, I was not planning on commenting on that, but I will then later when I again talk about the rigging and the bulk. This is just an example to give you a flavor. What you're saying is perfectly fine. So suppose you write now your metric in Newman-Penrose, you would write something like NL plus MN bar. Okay, sometimes KL. I mean, Newman pairs, the letters have been used in various different ways. These are the complexified objects down in the sphere, as you were saying. And then you have L that could be the intrinsic quantity, and then that could be the normal. And you can just do everything I just did in a much more general setup, of course. Now, this is true for any manifold. It doesn't have to be Minkowski. And you will get exactly by at the end taking the level sets for the one form, say, n to vanish, this construction. One subtlety to point out, since you're mentioning the general construction, is that right now in this little example, of course, my one form, which I call L here, is hypersurface orthogonal. And generally, a Newman-Perros one form, when you do decompose the metric, is not hypersurface orthogonal. So you're going to have to ask some conditions if you want to go back all the way to what I'm describing here. But what you're saying is perfectly valid. And indeed, the rigging construction we will see later has perfect application in the Newman-Perros of formalism. Okay?
Okay, thank you. Thank you.
Thank you. Other questions on this warm-up? Are we warmed up? Are we ready to do the whole thing? Okay, good. So, please, again, if you have a question, interrupt. Let me start with the whole thing. So the whole thing is geometry. Now, I don't want to know that there is a bulk. I don't want to talk about some embedded hypersurfaces. As I was saying, we can study pseudo-Riemannian and Riemannian manifold without talking about them embedded in an ambient space. So let's do the same for N. So N, which was the null hypersurface before, now becomes a null manifold on its own. So it's a D plus one dimensional null manifold. And I'm gonna dimensional manifold. And I'm gonna say what I mean by this carefully. By this, I mean that I'm endowing it with what is nowadays called a Carrollian structure. Carrollian structure. What did I write? This is the right word. And the Carrollian structure will be nothing more than, I'm going to call this C like this. It's going to be the specification of the manifold, QAB and LA, such that LA components of the vector are nowhere vanishing as components, as functions, and LA QAB equals 0, which enforces that QAB is degenerate with corank 1. Okay, so these are the conditions. Now, QAB and LA, they don't need to be very simple. They don't need to be d by dv, and QAB need to be 0 times something. They could be more complicated, right? This is just a general framework. It's like when you start from Minkowski and then you describe G mu nu for an arbitrary manifold, right? It's the general framework, this. Again, A and B are abstract index notations. So when you write something like this, everything is completely diffeomorphism invariant on this manifold N. There's no more bulk. I'm intrinsic now. Okay? Good. This enforces that QAB is degenerate. And let's see one first consequence of that being degenerate, which is I want to lower indices, right? That's what we do when we have a metric. We have vectors and then we have one forms, right? How do we do that? So for instance, let's do it with B itself, with L itself. I want to define LB down. What would you do? You would say, oh, this is, I act with the metric, with the vector. That's how I would define it. Here you see the first problem, right? We just wrote it 1 centimeter above. This is 0. So we don't have a metric dual one form to the vector because it's degenerate, right? There is nothing surprising, but this is the first thing we have to deal with. Okay, how do we deal with it? We deal with it by remembering that, sure, there is no metric dual, but we have tangent bundles. We always have one form and vectors, right? Those exist. Once n is given, exists the n and T star n. And there is a pairing, which is just a tangent bundle pairing. So what you can do is that you introduce, the only difference is that you have to introduce it by hand now, a one form, K, which is going to be therefore Ka dxa, such that La Ka is equal to 1. This is the tangent bundle dual of L, is not the metric dual of L. The former is well defined, the latter doesn't exist. Okay? And now, as I said, on the other hand, this must be introduced by hand because you don't have a metric. So this K is another object on its own. And therefore, sometimes we call the structure N, Q, L, and K. To give it a name, we call it sometimes a ruled Carrollian structure. And I can tell you why we use this word ruled is because we are thinking in terms of ruling, really like taking a rule and making measurements. Because what is this K doing, right? So this K is introducing for you the notion of level surfaces on the null manifold itself. For instance, this K in the example before could be taken to be dV, the one form dV, right? So the V equal constant are paths on this null manifold. And that's why we think of this as introducing a ruling. Right? That's the naming, okay? All right, so this is the structure. And now one question that you could have is, what are the symmetries? What are the ambiguities in the various objects, right? I mean, you just told me that K is independently defined, but it's defined only through this relationship. I should just use it, this relationship. So of course, for instance, and I'm calling this section symmetries in the sense of what I can change and have the same structure again. So for instance, we were talking, let's start even with the simplest one. Look at this equation, and L is nowhere vanishing. Well, which L? Of course, if I send L to an exponential of something times L to ensure that the multiplicative function is nowhere vanishing, that's why I'm putting an exponential, then the L prime A, Q, A, B is 0. And L prime is nowhere vanishing. So this is the first symmetry. This symmetry is sometimes called rescaling. So it's a rescaling of L. And strictly speaking, one should work with a conformal class of L under this rescaling. This is not surprising. It is simply stating in a different language the fact that on a null time evolution, the line element ds square is 0. If I take a geodesic that is on null, ds square is equal to 0. And so the intrinsic notion of null lengths is unphysical, right? It's conformal. I can rescale it as much as I want. This is that evidence geometrically. There's a second one, which is also kind of obvious, which is for the same reason we just talk about. You could rescale also this metric. It's the same reasoning. This equation is LA Q prime AB is still 0, as long as omega square is invertible. And this is more of a true, like, conformal class matrix discussion. And the final one is what I was just mentioning, which is LA KA equal 1 is preserved if I send K to K plus some one form zeta, as long as I ensure that zeta is in the kernel of L. And I'm going to start to write things like IL. This is the interior product, because I'm going to jog between the two notations. This, of course, just simply means LA zeta A. But I like to jog between the two notations so you start to get familiar with the fact that you can write things either in indices contraction or in a more, Partan language, if you prefer. Okay? This symmetry of K, of course, preserves the fact that K is the tangent bundle dual to L, and this is what sometimes it's called Carroll boost. Its global version, if you study algebraic groups, is really what generates the Carroll group, which is the limit C to 0 of the Lorentzian boosts. Okay? So these are the symmetries on the structure, symmetries in the sense I just said, and it will be an entire other talk and a very long appendix of the review just to keep these symmetries everywhere and make sure that everything I define as physical quantities should be invariant under all these symmetries. I will not do that. I will keep going on. I want to mention those to you, and they're very important to keep in mind. Okay? Okay.
May I ask another question?
You can.
So by saying that L can be rescaled as an exponential of lambda, we somehow imposing that the rule for K is the inverse of the exponential when it's scaled? How can we say that
Absolutely.
when L is so, but we somehow made up K, right? To be the somehow the dual tangent models element as a K.
Yeah.
But how can we sure that it's actually inverse of the exponential when it's scaled? How by just saying
Oh
that
no, you impose it, right? You impose that
impose
after
it.
that
Okay.
symmetry, you have to choose a different K. Absolutely right. That's a good question.
Okay.
Of course, these symmetries, they come with a bunch of equations that ensure. So you have to tell me how everything transform under these symmetries. And as you're pointing out correctly, you have to ensure that K transform in the opposite way so that L dot K is 1. Otherwise, that K is no more the tangent bundle dual of that new L. Yes, you have to transform K accordingly. That's a good point.
Thank you.
Thank you. Okay, so we started to talk about the fact that you might want to talk about cuts. The Carrollian structure is very rigid, right? There is this time, which is kind of God-given, is this L quantity, and then you have this metric that is degenerate. And so this naturally goes to the introduction of a projector. I want to be able to project the cuts, right? And the projector in this story is called QAB, and its definition, projectors are always defined as completeness relationship from the identity. That's always the same structure. We're going to see many of those. And this definition is simply KALB. Now, is this a projector? Let's show it together. Property of a projector you have to enforce is that QQ is equal to Q. Given the fact that LA KA is 1, this is pretty obvious. So please go through, and if you cannot show it, let me know, and I can show it to you. And then it projects where? Well, it's simple. You have to ask yourself, if I project the metric, since L dot Q is 0, this just give me the metric down, right? If I project the one form K, this is just KA minus KA, so this is 0. And if I project the vector L, this is LA, LC minus LC, which is again 0. So where does it project? It projects to the space orthogonal to L and K, right? Which is exactly where the cuts live. Now let me draw a picture. Let me suppose that my null manifold is something like this. I'm going to write these banana shape things like this, where I'm defining this direction as being spanned by the vector field L. In the example before, remember, this was partial V, but it doesn't have to. And then QAB projects to these cuts that I called C before. So let's take the very simple example again. The very simple example in which L is partial V. I'm going to choose K to be dV. This, of course, ensures that ILK is 1. I'm going to stop soon writing both indices and Cartan, and just we should understand that this means that. So this is a very simple choice that I'm making for this rule Carrollian structure. And then I'm taking Q to be exactly the Q I had before, the one with zeros and the solid angle metric down here. Then let's see what QAB is. QAB is equal to delta AB minus KALB. In this simple example, delta is, of course, just the arg1, so there are ones everywhere, minus this matrix. Now, this matrix, though, has only one entry, which is 1 in the VV component and 0 everywhere else. 1 and 0 everywhere else. So what is Q in this simple example? Q in this simple example is 0, 1, 1. Well, that is the projector to the base, right? It projects to the DSD2, sorry, to the solid angle. So that's the very concrete thing. But of course, this is a much more general definition that is true in any setup. Okay? It always projects. Okay, very good. So we have this projector. It's going to be useful because now I can talk about indices and raising and lowering. And let me also point out one thing. We just show it in this example. What is the trace of this object? The trace of this object is just the sum of ones on the space orthogonal to L and K, which is T. The trace of delta, the Kronecker, is just T plus 1, right? So this is going to be important in a moment when I'm going to define traceless and traceful components. Okay, beautiful. So let me do an example of raising and lowering, in quotation mark, indices with Q itself. So I have QAB. This object is degenerate. So I cannot just say QAB such that QAB, QBC is equal to delta CA. It doesn't admit an inverse, it's degenerate. So let me erase that, mathematically wrong. Let me talk about another object you can introduce, which is QAB, defined to satisfy the following properties. I'm going to say QAB, QBC is equal to the projector that I just introduced. And I'm going to define it to be orthogonal to K. Now, let's count how many conditions this gives. And it's not hard. This condition is not enough because the temporal part is not there. And this condition fixes the temporal part. And so Q AB up as a matrix now can be implicitly defined via these two conditions uniquely. What is this quantity? Well, this quantity, you should think of it as the partial inverse of QAB down. What does it mean partial? It's partial because it's the inverse with respect to the non-degenerate part. And the non-degenerate part is exactly the angular parts. What you do is that you project to the angular part, and then there you have a non-degenerate matrix, so you can raise a lower there. This is what this generic formalism is doing, right? So this is a way to, and really I put quotation marks every time I say it, because one should call this lower and raising and lowering indices. It's just a way to define object with mixed indices. Do we care? Yes, because we want to talk about traces. I cannot take a trace when I have an object with two indices down or two indices up. I need to talk about the mixed object. And I'm going to do an example right now, which is the most important tensor that you're going to define on the null hypersurf, a null manifold, which is the expansion tensor. The expansion tensor has various names.
I have a question.
Yes. Hi.
Sorry.
Yes.
Good morning. Good morning to everyone. Before to continue in the discussion, I would like to say you are taking the transformation or taking the change of coordinates using the spherical coordinates, but what it means the vector NA, you are calling NA? Yeah, this vector that is in some sense orthogonal to the metric, what will be this vector in the original flat Minkowski metric? It's not clear for me what is the
I'm
meaning
sorry,
of
but I don't know which vector you are asking. L or K?
LA.
L is partial V.
Partial B, but you are taking this partial B when you are changing the coordinates, right? You are using CT minus you are using a change of coordinates, right? In order to
Oh, you're
define.
asking what is partial V in these coordinates?
Okay, but what I am asking is what is the meaning of LA in the original coordinates? Not doing this change of coordinates.
Right. So L was TV, and then you rewrite it as dv of t dt plus dv r dr.
Okay.
Right? And then you invert this relationship that I had somewhere. I don't know where it is. What did I have here? And if you invert this, you get that t is u plus v over 2 times c, probably, if I'm not screwing this up. And r is just what I wrote before, which is u minus v over 2. So you go in. Let me just make some space where this has already been said. So you go in, you replace it. So what is dv of t? dv of t is 1 over 2c times partial t.
Okay.
And then you have dv of r, which is minus 1 over 2 dr. So the vector L in the original coordinate is 1/2. Let me put a c here. Partial t minus c partial r. Okay.
Okay. Still, I don't get the meaning or yeah.
The meaning. Great. Okay, the meaning is a different question. Very good. The meaning of this object. So what is happening? Suppose you want to work at u equal u0, and you rewrite it in the original coordinates. That's related to what you're saying. In the original coordinates, this condition means that c t equal r. So this hypersurface that you're describing is a surface for which ct equal r. What is that? As time augments, the radius augments at the speed of light. That is it's opposite of collapsing, expanding. That is an expanding spherical shell which moves at the speed of light. Right? So you could think of taking, let me give you a picture. You can think of having a sphere in Minkowski at fixed time, like this. And then you turn on time. Sorry, this should not be bent. It should be straight. I'm in Minkowski. You turn on time, and this thing, it just tells you bigger spheres as time evolve, and the time, and the radius of the sphere evolve at the speed of light. You can do the opposite. You can follow the vector minus partial v. That would be collapsing spherical shells at the speed of light. And now what is this object? This object is the vector that remains tangential to the evolution of the spheres. That is why it's not only partial t. Partial t will just go up. You have to correct it with the c partial r, so that this object is really the null vector field that follows this expanding or collapsing shells. That is the physics of L.
Okay, thanks.
No problem. Maybe I should have said this from the beginning. So thank you very much for the question. That hopefully helps clarifying.
Yes.
Okay. So I'm going to continue the second. So I'm going to talk about the expansion tensor, which is a crucial object. This the first time it is. Actually, this is a very old concept, right? I mean, all of these things have been said by many authors since many decades now. So I just say that sometimes you find it in the literature called the second fundamental tensor, and this object is very simple. It's called theta AB, and it is a half of the Lie derivative along L of the metric QAB. So let me make some comments. This is the definition. So let me make some comments about this object. 1, it is symmetric by construction. 2, it is fully intrinsic in the sense that I gave you L and Q. These were the Carrollian structures. You know theta. There is no extra ingredients. It's just completely given by the geometry of the null manifold. 3, it is orthogonal to L. Can someone prove that very fast? And since it's symmetric, I just do one index. So let me prove it very fast so you get familiarized with the kind of computations people do in this topic. Let me use this definition. I'm going to bring in L. And then this is 0, where I use two facts. I use first, LAQAB is 0. That's my condition on the metric being degenerate. And second, the Lie derivative of a vector along itself is 0 by construction. Right? So that's how you prove these kind of things, right? Okay, so symmetric, fully intrinsic, orthogonal to L. It being orthogonal to L makes our discussion of raising and lowering indices very simple. Theta AB is the unique tensor such that we just spoke about this, but I want to repeat it. Hopefully this is helpful. Theta AB QBC is equal to theta AC. If I re-bring the index down, I should hit the tensor with the index down, and theta AB KB is 0. Good. Now that I have this object, I can take theta AA. And so I'm going to give it a name. I'm going to call this object theta. And then theta AB can be always written as theta over D times QAB plus sigma AB, such that sigma AA is 0. What did I do? I decompose a tensor into trace and traceless parts. Now, important, why did I stick in a Q here instead of a delta? You would think that the traceless, the traceful part of this object should be something like delta AB over t plus 1. I stick in a Q because theta AB KB is 0. So this object really has a traceful and traceless part only in the space orthogonal to L and K, and that's why you get a Q over D. And remember, trace of Q is D. So that's what ensured this condition I just wrote here. That's why I stuck in a 1 over D in the denominator. Okay? Now, this object is well defined. The trace part is called expansion, and the trace free is called shear. Let me just tell you why they're called like that. What does it mean geometrically? Geometrically, this is very clear. The expansion scalar, what it's telling you is that if you have a sphere, and you're waiting enough time, you want to study how that sphere became a bigger sphere. Now, without twist, without vorticity, nothing. Expansion is really scalar. Each point just expands like this. This is controlled by the object theta. If theta is 0, this does not expand. There's no expansion. Right? Is it clear what I mean? Like really like expanding in a spherical symmetric sense. Just blowing it up is a scalar mode. Shear is not scalar. How many there are? Let's count. So sigma AB is a d plus 1 square entries. It's a d plus 1 times d plus 1 matrix, but it has a plethora of conditions: symmetric, traceless, and orthogonal to L and K. So let me do the very simple case in which D is 2, which means that the hypersurface is the null manifold is 3-dimensional. The bigger manifold would be 4. This is the usual case. If D is 2, this object, this object like this is, let me do it with the indices down, it's the same thing, is a 3x3 matrix, right? Then you have to impose that it's symmetric. Symmetric already tells you that you end up with, at best, 6 elements out of the 9 we started with. That's what symmetry imposes. And then you have to impose, on the other hand, that LA sigma B was 0. And this gives you three conditions more. You have 1 free index B. So orthogonal to L gives you -3. So the total amount here is 3. So it has 3 independent components. So if L is partial V, I'm just saying that these are the fixed by symmetry. And now let me assume that is also traceless. Sigma AA equals 0. This fixes one of the 2 components in the diagonal. So traceless is -1, which makes the total amount of degrees of freedom in this matrix 2. This is a shear, and it has 2 degrees of freedom. If you do, you just start from the bulk, a manifold, you do the Donder, traceless transverse gauge, perturbative gravity, this object contains exactly the gravitational wave modes, the H cross and the H plus plus minus H minus minus. So this object is the shear that you really see. The picture is, you start with your sphere, and the shearing mode, there are 2, are the sphere maintain the same volume. Notice that theta changed the volume here. The volume was increasing. This does not change the volume, so it just squashes it up like this, or it squashes it down like this. Yeah, of course, it does not become a square. It remains spherical here. Okay? These are the 2 modes of the shear. And you can really connect all of this with gravitational wave physics. That's not part of this lecture, of course, but it's an intrinsic Carrollian description to that phenomenon. Okay? And of course, both these quantities are determined by the fact that given QAB, so a metric on these spheres, you can determine how these evolve in time. It can shear, it can expand, it can twist. I'm going to talk about that later. Okay? Actually, I'm going to talk about that now. You might also wonder whether these things start to rotate in time in a certain way. And all of that information, on the other hand, is contained in the fact that the K object I introduced before, we have to study it a bit better, so I'm going to do it now. First of all, you might wonder, what is its exterior derivative? Its exterior derivative generically can be decomposed, and I'm going to tell you why. Now I'm going to treat this as a one form, and I'm using Cartan calculus. We warmed up that as well, into a two form var pi and a one form phi. What are these quantities? First, the one form phi is just related to LK. So again, since I'm trying to be pedagogical, I want to tell you, do a bit of computations. LK is the Lie derivative, it just do that, right? Then there are two terms. The first term is ILDK, and the second, but ILK is 1. So D of 1 is 0. So this term is not there. And therefore, I just have IL of dk. Now, if I take IL of this right-hand side, I'm going to get ILK, which is again 1. And then I'm going to get IL phi and IL pi, var pi. And I'm going to impose that these are 0, so that phi and var pi are orthogonal to L. And if I do that, the final answer is just minus phi. So this phi is sometimes called Carrollian acceleration, is the Lie derivative along L of this one form K. Phi is the Carrollian acceleration. This tells you as you move in time, how you rotate in space. And then the last one is var pi. I didn't tell you what var pi is. And now I'm going to talk about Frobenius. We said before, there was a couple of questions that actually were already related to this, which is important to enforce that one forms can be hypersurface orthogonal or not. Let me tell you mathematically what it means, hypersurface orthogonality. Hypersurface orthogonality mathematically means that if you solve for the level set of that one form being 0 somewhere, that somewhere defines a manifold. That is not true in general. Right? You can take objects that the 0 level sets can be discontinuous, disconnected, not topologically complete, etc. So for objects for which this is true, the level sets define a manifold, we call those hypersurface orthogonal. The condition for that to be true is called Frobenius theorem, Frobenius condition. I keep forgetting the spelling of Frobenius, but I think maybe... Okay, I keep forgetting it. I'm sorry. So I think it's Frobenius. I'm going to just do it like this. Apologies if there's a typo there. Theorem. Frobenius theorem is the following statement. If a one form, and of course I'm going to do it for K now for specificity, K satisfies dk wedge K, which is a three-form statement, equal to 0, then, or if you want, actually the converse is also true, K is hypersurface orthogonal. Which means the level sets of K defines a manifold. And that is the manifold defined at K, U equal constant, V equal constant, L equal constant, you decide the variables, right? This is a very general statement. Okay, now let's compute that for our K. So if I do K wedge dk, if I'm going too slow, you can stop me. I'm trying to be very pedagogical, but if it's becoming too pedantic, please feel free to just say, Luca, we know all of this math, let's move on. Wedge K is 0, of course. And therefore, you get just minus K wedge var pi. So, statement of Frobenius, var pi equals 0, then K hypersurface orthogonal. So what is var pi? Var pi as a name is called Carrollian vorticity. It is really a vorticity in the sense of you can imagine having these spheres starting to shearing and to rotating, and they can have holes, right? You can imagine this picture of vortices around. And if it has hole, it's not hypersurface orthogonal. That's why this vorticity, intuitively from a hydrodynamic language, controls the non-integrability of K. I'm sorry, maybe I should have said that. This is also a synonym of this means is integrability. There's a language, it's the theory of screening distributions. And so when I say hypersurface orthogonal or integrable as a distribution, I mean the same thing. They're synonyms. Sorry, sometimes I mix them up. Okay, and actually this points towards something very nice. This is something we understood 7 years ago, which is that all this can be reformulated in a very nice way as a fiber bundle. Now, I'm going to do an excursus, 5 minutes of that. Maybe it's going to be a bit technical, but the fiber bundle language is just, you have a projector from N to some base manifold, I'm going to call that S, such that the span of the vector field L, which is by construction in the kernel of the push forward of the projector, defines a vertical subbundle. Then Tn as a tangent bundle on its own can be decomposed into V plus something that is not V. Right? V the vertical plus something that is not V. But that something that is not V is ambiguous. That is known as the horizontal subbundle. And that is the reason why you have to introduce K by hand. It's not given from L and Q. You need to define a notion of horizontality. How do you define a notion of horizontality? Well, X as a vector field lives in K, if and only if Kx, which is Ixk, which is Xaka, is 0. You introduce a one-form K, you require something to be in the kernel of that K in order for it to be horizontal. This is, of course, ambiguous. For people that are familiar, if all of this was just a principal bundle, I'm talking about a gauge connection on a principal bundle. It's the exact same math. For those of you that are not familiar, forget what I just said. I'm just defining the fact that, of course, null time is so special that there is a fiber bundle structure associated to it. And the ambiguity of K is exactly related to the fact that I had the shift symmetry, that I could send K to something orthogonal to L. And this object indeed can be mathematically understood as what is known as Charles-Ehresmann connection. And there is some beautiful differential geometry you can do. Technical excursus, I just wanted to point that out for those of you that are mathematically inclined, and then I'm going to move on. Okay, I move on by talking about horizontality and verticality. I just spoke about that, and now let me just tell you it's important. How do I know that a vector, you remember we were solving equations like LA theta B equals 0, and then we say, oh, theta is orthogonal to L. Yeah, that means that there is a split between vertical and horizontal objects, or tangential and transversal, and that's very easy. Horizontal for a vector field means Xaka is 0. Then if you do that, you stick in the projector. Remember the projector was delta minus K dot L. You stick in a projector, that condition I just wrote implied that this is equal to XB. The horizontal component of an horizontal vector is the vector itself. That's what this equation is telling you. And now vertical is the opposite. And if you do that, then what you can write is that XA is equal to XBKB times LA. If it is vertical, must be proportional to L, because the vertical subbundle is the span of L. So what we found out is that, and when you do this kind of math, it's going to be very useful, this statement. We found out a decomposition. So every object, I didn't mean to write another XK. Every object can be decomposed in orthogonal or tangential and transverse space to L and K. A vector, and the generic one form does exactly the same thing. Okay. A bit technical, maybe. Just recall yourself with a very simple example we did at the beginning. If L is partial V, K is dV, I'm sorry, and Q is the diagonal 0, 1, 1. Remember, we wrote all of this. Then what is for any x, xa, ka? Well, it's just the V component. It's xv. That's what it is. And what is xa, qab? Well, you take all the vector and you stick in diagonal 0, 1, 1, 1. So it projects to the components orthogonal to V, right? And then what you're writing is that x is equal to xv partial V as x. Of course, in this example, this is super simple. But in general, this is a hard thing to do, right? A general decomposition like this. And so this is the, if you want, the general invariant way to decompose things. Okay? All right. So this closes actually all the geometric overview. I know I've been a bit long, but hopefully this is useful, and I decided to really take it slow so that you guys can follow. And if you're okay with that and you don't have questions, I want to talk about connections now.
Can I ask one question?
Absolutely.
So, you were talking about the Ehresmann connections. Is there any like physically intrinsic Lagrangian that we can write with these objects? Or
yeah, there are many Lagrangians that you can think of writing down with these objects. Yes. I can point out to some papers later. Yes.
Okay.
Geometric Lagrangians, absolutely.
Okay.
Yeah. I on top of my hand, I let to think about. I don't want to write one down because I'm sure I will not remember the details, but I can point out to the references if you want.
Okay, thank you.
Okay. I'm taking your words by literally, guys, that I can go on. So that's why I'm being very slow. I want really to convey messages rather than go fast and then you got lost completely from the very beginning and you don't follow. I prefer to take my time. And now I'm going to talk about connections.
Just one comment.
Please. Absolutely.
First of all, your presentation was very, very, very pedagogical, and I loved it. And
Thanks.
This is basically you're reviewing the geometry of null or any other textbook. Great. Like there is nothing particularly. So I mean, the Carrollian is still to come, right?
You
hear me?
you come and go. I cannot hear you very well, but if I understood what you're asking is this the standard material? And the answer is yes. So the Carrollian structure and root Carrollian structure are modern formulation of the intrinsic language. Of course, this can be described an embedded hypersurface in a bigger manifold that is, for instance, a black hole horizon. I think you mentioned those words. I'm not sure because you were glitching. From the intrinsic perspective, this language has been established in 1979. So there is really nothing very recent and new, right? I'm giving you a more modern way of understanding these things. But of course, this dates back to many, many years ago.
Sure.
Okay,
thanks.
No problem. Okay, and indeed, the connections, the statement I'm making now has been understood in 1961. But as I was saying, surprisingly enough, many physicists that had the experience to encounter don't know this statement and sometimes are a bit confused with connections. And so I really want to take my time to clarify it. The big statement is that Levi-Civita theorem on a null manifold, so let me just call that N, fails. And I'm going to just explain very well what I mean by that, with all the details, okay? So first, I'm going to review what the Levi-Civita theorem is on pseudo-Riemannian manifolds with invertible metrics and where everything is well-defined. And then, well, It's also well defined on Carrollian, but and then I'm gonna move to null manifolds and show what it means for that theorem to fail. I want to upgrade the language and use some more differential geometry notation. I'm gonna write it down and you guys tell me if it's clear or not. I'm gonna write maybe an equation. So for instance, what I'm gonna say is that if I have two vector fields, now I'm gonna review the pseudo-Riemannian case. Pseudo-Riemannian case, by which I mean that I'm on a manifold M that is endowed with the metric which is fully non-degenerate. So if I give you two vector fields and the bilinear form G, I'm gonna use this notation. By this, I mean something very simple. I'm going to use indices M and N for this bigger space now, just to make sure that there is no confusion with the Carrollian discussion later. Right? It's just the interior, the metric product of the two. But I like that notation a bit better. Why? Because it's going to be easier for what I'm going to do. And in particular, I'm going to work in a non necessarily holonomic base. So my base is going to be EM. And of course, if EM is d by dxm, then EM is a holonomic basis. But I really want to give you a more general proof. Since this is very standard textbook material, I want to at least give you the general one. And I hope it's not overwhelmingly complicated. I'm going to not assume that in general. So EM is not partial M. There's going to be a non-trivial commutator and structure constants. I'm going to talk about that in a moment. And I hope all is clear. And the metric I'm going to write is the metric in the non-holonomic basis. So G of X, comma, an entry is nothing but G of X, M, E, M, comma, an entry. Metric is a bilinear affine form. By affinity, just means that functions pull out like this. And this defines for me that quantity, right? Such that if I stick in another vector, I can get back to this formula. Is the notation clear? Please, if it's not, let me know. This is the usual notation.
I have a question, but not GMN is reserved when you are taking the partials derivatives, or GRN?
No, great point. Thank you. So what I mean is that now I'm defining this symbol.
Okay. Okay.
If E is partial, this is the same as the partial ones, but this is the metric in the frame bundle.
Mm-hmm. Yes, because it could be a little confusing. No, usually we are taking this as the definition when you are taking the partial, but when okay.
Exactly. Yeah, that's why I want to explain the formalism well. This is what I mean. So I hope it's clear. Okay, good. Now, let me define what an affine connection is. This is not Levi-Civita. It's just an affine connection. An affine connection is any object nabla such that nabla fx is equal to f nabla x, and nabla along x of fy is equal to f nabla xy plus x of fy. For f a function and x and y vectors. Is it all clear? X of f, application of a vector on a function is xm, sorry, not partial. We just spoke about that. Em acting on f. It should be very simple. So if it's not clear, it's because I'm explaining it poorly. So stop me if it's not clear. Okay, now this is an affine connection. For the moment, that object is completely general. The only property is affinity. And now let me talk about two important properties. The first one is the torsion of nabla. The torsion of the connection is defined in this way, is T. It takes two vectors and they spit a vector out. Nabla xy minus nabla yx minus xy. The torsion is affine. T of fxy equal t of xfy equal f of tx. And this is exactly the reason why, by the way, you have this extra term here. This extra term just ensures, given this property, that this holds, that affinity holds. You can just do the computation, you stuck in an f. If f is up here, it keeps up an extra term, which is exactly cancelled by the commutator to ensure affinity. This is the torsion. It's the usual thing. The usual thing that if you write it down to the coordinate basis, just tells you that the anti-symmetric part of the Christoffel symbol should be 0. Is that the thing that you see in school? But I'm just rewriting it in a more fancy way. And the second vector I'm going to care about is metricity. I'm going to call the torsion equation T, and I'm going to call the metricity equation M, because I'm going to use both of them. And metricity is nabla x gyz equal x acting on gyz minus g nabla x yz minus g y nabla x z. Is the usual non-metricity equation. I'm writing nabla mu of g alpha beta, right? It's just written in a more generic way. Okay, and then I'm going to introduce symbols, the affine symbols. Symbols just, you should think about Christoffels. Later they will become Christoffels. And they're just introduced in the usual way to definition. Okay? The gammas are the affine symbols. If I impose the Levi-Civita theorem, they become what is known as the Christoffel symbols. And again, I'm working in a non-holonomic basis. I want to insist on that. So if I take the commutator of these two quantities, it's not 0. It's 0 if they are partials, but if it's not partial, it's not 0. And I'm going to introduce structure constants. Okay? Then, theorem, which I can actually prove in case you want, but I won't do the details unless it's specifically required. E nabla, affine connection, satisfying is unique and given by and this is the famous formula we're all familiar with. I'm going to just add the first, I'm going to write it in a non-holonomic basis. This is hopefully something you've seen, but otherwise it's trivial. I'm just replacing partials with e's. But then, importantly, of course, there are all the other terms that come from the structure constant of the basis I've chosen. Okay, so if E is partial, I just wrote down the Christoffel symbols that we are all familiar with. C is 0, E becomes partial, and etc. This is just expressing the general one. Okay, but what is crucial about this is, one, I used the inverse. So in a Carrollian thing, we're going to see this is subtle. But two, even more importantly than that, when I solve T and M, the torsionless and metricity equations, so when I impose them equal to 0, those were conditions, if I stick in the affine symbols, those were non-trivial equations relating the symbols and the metric. The fact that the solution was all the symbols are written as a function of the metric only, it's completely an accident. It's a remarkable thing of the equations. There is no guarantee a priori that those equations should have this solution. You could define a condition on G. You could define that the system is not solvable. It just happens by the specificity of the computation, which again we can do, but I'm sure you're familiar with, is the usual computation, that you find that gamma can be solved exclusively as a function of G. Solved for gamma of G. right? We're gonna see in a second why I insist on that. On the null, so on a degenerate manifold, this is fails. This is no more true. Just the structure of the equation doesn't allow you to do that. Okay? Just to point out that given all of this, the Riemann tensor is defined in the usual way. You stick in a vector. I think it's n. Yes, it's n. And this is just nabla p, nabla q, xm. Right? That's the usual definition. And just in case you haven't seen this non-holonomic formalism and you guys want to, since this is recorded, you want to retake this. I mean, they're also in my review, you can find them there, but just for completeness, let me write down how it looks like. It's a very simple equation. So this is the usual Riemann tensor. And the first terms are the things you're familiar with, hopefully. There is nothing surprising. It's just gamma, gamma, etc., etc. SMQ, sorry, give you the right index structure, SPM minus gamma. And when you write it in a non-holonomic basis, there's actually only one extra term, which I'm going to write here, which is just C, P, Q, S. This enforces that this is antisymmetric in these indices, remember, by definition, S and M. That's it. That's the Riemann, okay, in the full non-holonomic basis. So it's an exercise to derive it from what I just wrote and this Christoffel. It's a funny exercise. Okay? Good. Now, Carroll. Oops, I don't want to do it. Carroll. Well, let's just do it, right? So I'm going to make my life as easy as possible. We were working in abstract index notation, XA, but actually I was working implicitly. Of course, I was working in an holonomic base. I wrote things like that before, and I'm going to stick with that. I don't want to write the more general one. And if I stick with that, the more general one is in the review. If I stick with that, partial A, partial B is obviously 0, and then CA, BC are 0. So no structural constants. So it's the usual holonomic base discussion. I am on my intrinsic Carrollian manifold N. My coordinates are XA. And I introduce an affine connection, DA. Oh, by the way, up here sometimes I wrote nabla. You see here I wrote nabla sub EM, but that's what, of course, we write nabla M, just to make sure the notation is clear. So down below, when I write dA, I mean d partial A is the usual notation. Okay, so if you introduce the affine connection dA, you can write down what the torsion is. And again, I'm going to stick in with basis indices. And then this is just dA partial B minus dB partial A. Remember that the connection symbol are defined as dA partial B is equal to gamma ABC partial C. This equation that I just wrote, this means an application, of course. This equation that I just wrote is just this equation for the basis itself. And so you just stick in. The commutator partial A, partial B was 0. So let me write it down and insist on that. I just say that is 0. And so the connection, the torsion just become very familiar statement, gamma ABC minus gamma BAC partial C, which is just twice gamma ABC. Square bracket is anti-symmetry and it has a 1/2 in my conventions. Okay? Very familiar. That's the torsion. And now let's do the non-metricity. dA, Q, partial B, partial C. If you channel this through, you want me to show the details? I mean, yeah, sure, it's not that hard. So I'm going to show it. So it's partial A, Q, B, C. Of course, I defined Q, B, C as we already spoke about as this. I'm using the definition I gave you above, minus Q, dA partial B, partial C, minus Q, dB, dA partial C. Now, these are the gammas. This is gamma A, B, D, partial D. And remember, is affine. The Q is affine, so the gamma pulls out. So the only things I get is dA QBC minus gamma A, B, D, Q, TC. minus gamma ACD QBD. Just to familiarize yourself, this is the very well-known equation, right? That's how the covariant derivative acts on the metric, right? Good. So I'm going to give names to these objects. So I'm going to call the components of the torsion T, A, B, C. And I'm going to call this object N, A, B, C. T as torsion, N as non-metricity. Of course, N is just dA QBC, but it's going to be easier to write the equations this way. And now the Levi-Civita statement is that if you impose N equals 0 and T equals 0, you solve for these gammas as a function of Q. But now let me show you how it fails. First, and this is just a little computation, I'm going to compute, and I'm going to do so introduce a notation, this contraction. So when I put an L as an index, I mean that this is the contraction with L. It's just, I'm defining that notation. Is that clear? So when I put an L as an index, I mean just LA and ABC. Now, if you compute that, this is just LA partial A QBC minus LA times gamma ABD QDC plus gamma ACD QBD. And now I'm going to compute a second contraction, 2. I'm going to compute N, A, B, L, which I remind you is just N, A, B, C, L, C. Now, careful. What is this? This is L, C, D, A, Q, B, C minus, I'm going to do it slow to tell you, this is exactly the moment in which that theorem fails. Okay, I just wrote down what it is. But now, do you notice something? I'm gonna... What is this?
0.
0. Exactly. This is the moment, the exact moment in which the Levi-Civita theorem on a degenerate structure fails. Is that 0? Prevents you in the solution of N equals 0, T equals 0 to solve for gamma as a function of Q. You don't have enough freedom. And so this is LC, dA, QBC minus gamma AC, D, QBD. And now I want to show you, I'm sorry, in all of this I forgot an LC down here, thank you. Now I want to show you exactly that computation, but this was the moment. This is the step. And now I'm going to show you in which sense it fails. And you will see something nice. So let me define the third object, which is TL, BC, or better AB. I brought the index down of T here with Q. So I'm going to define what is this object. Is LC, T, C, A, D, Q, DB. That's the definition. And if you compute this guy, it's very simple. It's LC gamma CAD Q DB minus LC gamma ACD Q DB. Okay? Okay, I have 1, 2, 3. And now I ask you, I'm going to do the computation with you. Compute N LAB minus 2, the symmetric part in the AB indices of N and ABL, plus 2, the symmetric part of TL AB. Okay, you combine with these 3 tensors I just computed this, and you make this sum. You can go slow. The first term, this guy, I'm going to call it L acting on Q. I hope that this notation is by now understood. So L QBC. And then you have minus 2 LC. Let me go slow. Yes, gamma C A D Q B D. This is just a quick rewriting on this, right? And then you have minus 2 LC D A Q B C And then you have plus 2 gamma A, C, D, Q, P, D, LC, plus 2 LC, gamma, C, A, D, Q, P, D. And the last term is minus 2 LC, gamma, A, C, D, Q, B, D. Now, what happened? This object, which was here, gave me these two terms. Very clear. This object, which I'm taking minus 2 times the symmetrization, gives me minus 2 the symmetrization of this, which is this, minus 2 the symmetrization of this, which is this, with a plus. And finally, this object gives me these two terms. Okay? Now, this is exactly the moment in which, because if you do the same computation for a non-degenerate, you add this extra term. Because you don't have this extra term, this is the moment in which you just get that this cancels with this, and this cancels with that. Right? Exactly. So the final answer is that these three objects are L QBC minus 2 LC partial A Q BC. No more gammas. Do you know what this guy is? Oh. Yeah,
The
let me
Lie
do another.
derivative.
Yes, thank you. I wanted to show it with another step, but you got it already. Right? Now you're going to use that LCQBC0. You can rewrite this as LQBC plus 2 QCB DALC. And this should be a more familiar expression, but you already guess it. It's just Lie LQBC. So we find NLAB minus 2 NABL plus 2T LAB is equal to the derivative of Q. Oops. Just to make completely sure I'm not screwing up, this is AB indices. And I just realized that this was AB. I just have a messed up index on this term. Apologies about it. Let me fix it quickly. AB, AB, AB. And this is AB. Sorry about that. Okay, so this is failure of Levi-Civita. Now suppose your Levi-Civita, you want to impose n equals 0 and t equals 0. This is metricity and torsionless. Then the derivative along L of Q is 0. But wait a minute, but I thought you wanted to find the most general symbols. You didn't want to find the condition on the geometry itself. This is exactly what we mean and what mathematicians mean when they say on the degenerate manifold there's no Levi-Civita theorem. Let me explicitly say it again. You cannot impose metricity and torsionless without constraining the metric itself. As I'm going to show in a moment, some of the affine symbols, therefore, are left undetermined. And again, it's because there are some very non-trivial cancellations. Okay? So either you impose no metricity or you impose torsionless. You can choose to do that. You can even choose to work with the most general one, but you cannot impose them both. Now you can ask yourself, is there a preferred Carrollian connection? DGA is what we call a Carrollian connection. Well, obviously, if the metric is time independent, LLQAB is 0, and then you can do Levi-Civita again. If you are in the background where the metric is time independent, you can do Levi-Civita. You can impose n and t equals 0, and there is a preferred one. In the most general situation, it's your choice. And what I want to talk next is that there is a preferred connection if you now embed this null hypersurface into a bulk. From the intrinsic perspective, there isn't. This is the most general structure. You do what you prefer with it. But if you embed this null hypersurface in a bigger manifold, you can use the bulk Levi-Civita connection to induce the connection that you would like. And that is a very specific connection, which has beautiful properties. And that's the one I want to move to next. And this brings me to embedding all this intrinsic formalism. There were no bulk in what I said so far, if this null manifold is embedded as a null hypersurface. Okay, I'm really going slow because I want you to stay with me, and I appreciate that maybe this might be a bit overwhelming because a lot of details, but I hope that at least, this is made precise, right? It's not some vague statements now, okay? And I have been talking for what, 1 hour and a half? Oh, wow. So the next step, I want to talk about the rigging and the bulk. I think that if I cover all the material that I still have, it's going to be too much, even considering how generous you are. I know the sky is the limit, but we'll probably reach the sky if you don't stop me at a certain point. So I'm going to try to go through the rigging quite fast. Because this talk and this lecture is supposed to be about Carrollian physics, so I want to introduce the rigging as a tool to go back to Carrollian, and so I'm going to try to do that. However, so I'm going to speed up. It's going to be less pedagogical. If it is really too much abstract and fast, you stop me and we can take the time we need. Okay?
Okay, we can go with that.
Fantastic. Okay, now let me go back to the bulk. So I have a null manifold, which was my bananas. And now I put my bananas into some bigger blobs, which is the bulk M. So remember, the notation was always the same. D-dimensional cut, D plus 1-dimensional null hypersurfaces, D plus 2-dimensional bulks. Okay, now I want to study this a bit better. And so how I'm going to define the embedding, I'm going to go through the normal one form. X mu are bulk indices, XA are indices on N. So I'm going to introduce the normal one form to the surface, N. And this, for instance, in this very simple example we were doing before, would be du, what I call du, but it can be much more general. However, in order to N to a hyper, so in order to N to be a hypersurface, N must be hypersurface orthogonal. And so remember, it has to solve Frobenius. And so I'm going to impose that dn wedge N is 0. Okay? Now, how is the surface? Is the surface time-like, space-like, or null? This is controlled by the norm of N in the bulk. You can compute N mu, G mu nu. The bulk is pseudo-Riemannian, it's not null. M is pseudo-Riemannian, so there is a metric, G, invertible, well-defined, as usual. And now, if this is positive, the surface is time-like. If this is negative, the surface is space-like. Remember, it's always the opposite, right? And if this is null, the surface is null. And that's exactly what we're going to impose. We're going to impose that our surface N is null. Okay? So in the case before, for instance, you remember du, if you take N equal du and you take the vector was partial V, the vector belongs to this, and N is obviously 0. So it's exactly like that, but in a more general frame. Okay? And now the whole point is that since the metric dual of this object is actually d by dv, not d by du, so it becomes the vector on the surface. This is again the magic of null physics, in which things keep swapping around. It's not enough to just give the normal one form. You need to introduce an auxiliary vector in the bulk to define well projectors to the surface. The auxiliary vector in the bulk, which in the example of before is pretty clear, I'm going to call that vector k, would be just d by du, is what is the rigging vector is called. So the rigging procedure of the rigging vector is an auxiliary, meaning you have to specify it yourself. It's not given by the normal. It's an auxiliary vector k in the bulk. Of course, everything is in the bulk here, satisfying And now you will see that all the discussion we had so far was really propedeutic to this. K mu and mu is 1. So it's the same story again. Metric duality in the presence of null vectors in one form is tricky, and you also use tangent bundle dualities. Okay, so this is the vector field, n as norm 0, and k as a free norm, but I'm going to impose that it has norm 0, and this is what is called null rigging. So I'm going to work in the framework of an R rigging, for instance, partial U in that case before. So also k will have 0 norm. Okay? Then if you do all of this, you have a projector to the hypersurface from the manifold. This is called the rigging projector. Pi mu nu. As always, it is a completeness of the identity. It's always the same. Projectors are always that. Delta mu minus m mu k nu. Properties. Pi is pi. And then it is a projector, pi square equal pi. And then where does it project? Pi mu nu and nu is equal to 0. And so is k mu pi mu nu. And then pi mu nu k nu is equal to k mu. Let me know if these are unclear statements. I can show you the details, but it should be pretty obvious. N mu nu and nu is n nu. So it projects to the space orthogonal to n down and k up, and it projects as the identity to the space generated by k down and n up. So n down and k up are extrinsic data, they project as 0. And on the other hand, k down and then up, intrinsic. Where does it project? It projects on n. So I is a projector to n. Take the very simple cases before. Remember, in the simple cases before, n down was du. N up was partial v. K up was partial u. Remember, n dot k in the bulk is equal to 1. And k down is dv. So the projector kills these guys and projects the identity with these guys. Well, it's pretty much what I would like it to do to project into n, right? Okay, so if you give me that, next step is I want to talk about moving from coordinates in the bulk to coordinates in n. To do so, I have to introduce an inclusion map, which maps one to the other. The inclusion map goes, of course, in the sense from the smaller fish to the bigger fish, always. And because it's including, what it does is that if you take the push forward, it takes your coordinate basis partial A, and it includes it, or it lifts it up to M as EA mu partial mu. That's what an inclusion is, right? I'm just talking between coordinates intrinsic to n and coordinates in the bulk. Okay? And now I want to study the dual map. And for sure, what I can impose is the following. I can impose that if I trace over the bulk, so if I go to the bulk and then I go back to the surface, this can be the inverse, right? That I can impose. But now the opposite is complicated to impose, because what happens if you contract the smaller indices, right? You get something in the bulk, you don't know that that's delta. And so now I want to talk on how to do that. So this E A mu has, you know that I like the counting, so it's d plus 2 times d plus 1 components. One index is d plus 1 and the other index is d plus 2, right? This obviously provides a d plus 1 times d plus 1 constraints to it. So d plus 2, d plus 1 minus d plus 1 squared is just equal to d plus 1, which means that this matrix, so this matrix is given, is part of the inclusion. And then I want to study the dual, which is this. And this has d plus 1. Yeah, so I'm sorry, I wrote it wrong. I mean, of course, I meant that I want to determine this object. Sorry about that. It could have been confusing. Is it clear, the logic? This is given by the inclusion, and I want to study the dual map. And to do that, I can, of course, impose this, because it's an improperty intrinsic on n. I go up and then I go back. I want identity. But that's not enough. I still have d plus 1 independent components to fix. What fixes them? It's your choice, but that's another way in which the Null rigging is very useful. K mu E mu A. By construction, if these guys bring me back, I can ask it, K up, remember, was an extrinsic data, to be 0. It's very similar to what we were doing intrinsically with the projector QAB, right? If you remember before. How many conditions? D plus 1. The index A has D plus 1 components. So that fixes E mu A uniquely. I wanted to go through this detail because I want to explain you what I did. Now, take a vector in the bulk and write it as, therefore, I project down using this map I just determined. I project back up. And then, since this is orthogonal to K, and K is the tangent bounded dual of N, I can stick in this. Remember, I spent a lot of time telling you before, intrinsically on N, how to talk about horizontal and vertical. This is the same kind of concept, but in the bulk now, right? But if you notice what this is just X, E nu A, E A mu, plus N nu K mu, and just wrote that X mu is equal to this, which means that this is a completion of the identity. Is delta mu mu. There is how to find out what E mu A, E A mu is. This is delta mu mu minus N nu K mu. But thanks to the choice I made here, thanks to the Null rigging, what is that? It's the projector. It's pi itself. So what we found is that the contraction EA mu is equal to pi mu mu. So now I have a way to talk about indices in the bulk, indices in the surface, completely invariant, completely well-defined, very natural given the rigging. E A mu E mu B is delta AB, and E mu A E A nu is pi mu nu. That's it. And in particular, since pi is a projector, you can ask yourself now, what is pi A mu? Well, now you have a way to define how to pull to lift and bring back indices. So just by that, I just applying the notation I just find is this. Of course, because this E now brings the indices, move the indices. But now if you write down this explicitly, this is E A nu, E nu B, E B mu, I suppose that's the last index that remains. But now this, you can use the other completion. And what you find is that this is E A nu. Perfect. Projecting and stripping off the bulk index is exactly the map E. That's what pi is doing when you stick in an A. Is that clear? This is not true in general. It's true given the assumptions I made to solve it, right? The E inverse. Because remember, there is this E appearing here, right? That was solved through the assumptions. So we call this object soldering, but you can forget about the name. Okay, now finally I can tell you what are the induced quantities. LA is you evaluate on N the projector, the projected version of N. KA is you evaluated on N the projected version of K. It's important, the index placement. And QAB you evaluate it on N, the projector of the bulk metric. Pi project to A, to N, pi project to N, and little ab strips off the bulk index. So this define for you what? LKQ ruled Carrollian structure. So the very intrinsic and completely agnostic of the bulk discussion we had 1 hour ago is in completely nicely induced from the bulk, if you have an ambient space, through this null rigging procedure. Is that clear? So that's what I set up. And once I have that, now I can go a bit faster because I will not give you the details. Those are messy. Once I have told you how to induce the geometry, I can induce the connection. And that was the last point that I had before that I couldn't finish because I didn't have a preferred connection, but now there is a preferred one. What do? It's the usual story. For every tensor of indices B and C, you stack in all the pi's.
Sorry.
And yeah. Please. No, actually, no. Just give me a second because this is a very important step. So I'm going to just finish it and then I'll give you the, sorry about that. So it's times pi. I suppose I want to call this alpha C dot times nabla mu T nu dot alpha dot. This is just the projector of the bulk Levi-Civita connection acting on a bulk tensor. T is a bulk tensor. T, B, C, etc., is pi T. We have found how to do that, right? We just spoke about it here for some specific cases. And this defines for you, so you should think of this as, since this is very uniquely and unambiguously defined, is the torsionless and metric compatible connection in the bulk. You should think of this as defining for you dA induced. Sometimes I like to call this a preferred, because obviously preferred for this kind of physics, Carrollian connection. It defines how that things act. Please, there was a question.
Yes, sorry.
No problem.
Yeah, I get lost a little. If you're taking a picture about and try to make a figure, the vector n and
Oh,
k
yeah, very good.
they are null because his measure is 0, but they are not orthogonal because his measure is 1. So it's not clear for me how it's related. It seems that both of them should be equal 0 vectors. His measure should be 0.
Yeah, so let's do the simple case of Minkowski just to make you familiarize, because this is a physical intuition question. You want a picture. Then you can draw the picture in general. In the Minkowski guy, remember you had K was partial U, N was partial V as vectors, and as one forms, K was dV, and N was du. Okay, so this was the picture. Now let me draw the vectors here. I draw N, the surface. Coordinates on N are V, comma, the base. Coordinates on M are U, comma, V, comma, the base. And then, and it's very tricky to draw vectors when they're null, right? Because the fact that they are, their norm is 0 is what you're saying is complicated. But this is a pictorial picture. So take it really with a grain of salt. And here, this is very pictorial. But the idea is that the normal vector is going to be du, and the intrinsic vector, and I should draw this in yellow, is going to be dv. So n lives here, and k lives here. Now, what is tricky about all of this is that if you think about the dual one forms, the metric dual one forms, the opposite happens. So, of course, you cannot draw one forms as arrows, but just pictorially again, if you want to draw the one form picture, the thing that we point out is n. That is the one form normal to the surface. And the thing that would point in is what I call K.
Okay, yes. And both of them have to be norm zero, right?
By choice that I made, yes. And N is by construction, otherwise the surface is not null. K could be not norm zero, but I'm choosing it to be norm zero.
Okay, and the other equation that you write before was that k n mu k mu the contraction should be 1.
Yeah.
This means that they are not orthogonal, and that what must say that
Yeah,
they
so this means that the vector K and the one form N are not orthogonal,
are not orthogonal, right?
which is true. Where they are, take the vector K and take the one form N. They're not orthogonal. Again, I'm not allowed to draw this, right? So I'm making an exception here by drawing one forms and vectors in the same plane. I just want to give you an intuition. It's
Yeah.
true. K as a vector and N as a one form are not orthogonal.
Yeah.
It's very
Okay.
important. It's very important in this picture that tangent bundle duality versus metric duality is a different concept. Of course, it's always true, but it's important to keep that in mind. You see, they're swapping roles. That's exactly why, by the way, you need a Riemann vector. Because if you don't introduce an eigenvector, you start with n, which is normal to the surface as a one form. You take the metric dual, and you get something that is tangential to the surface. But then you don't have a way to describe the vectors that points out. That's why the rigging comes in.
Yeah, but both of them are light vectors.
Yes.
So it's interesting, no? Right. The physical formulation.
It's very interesting. And the more you think about it, the more you get confused. But you're just stating that sometimes in the literature you find statements like that vector is at the same time normal and tangent to the surface. I don't like those statements. I see why they made it, because what do they say? The vector is normal, then you take the metric dual and it's tangent. So I see why those statements are made, but personally, I'm not a big fan of those statements, and that's why I want to explain it with this intuition. And as you're saying, it's extremely interesting. I mean, you can think about it forever.
Yeah. Thanks.
No problem. Okay, so is this clear? I'm defining now the connection that I like this way, and I'm gonna give you all the properties, if that's okay. So what are the properties of that object? First, let me compute T, A, B, C. By the way, now I know we are all getting tired. I've been speaking 2 hours. It's really a lot. Sorry about that. So when I say compute, I'm not going to show you the detail. I'm just giving you answers. Details are on the review. I just want to get to the final punchline, which I think is interesting. Please stop me if you're really getting too much. No problem. Okay. So first, properties of this D. dA, which is, I sometimes write this when I explain it to my friends informally. D is pi of nabla. What are the properties of this object? The first one is, if you compute the torsion, the definition of the torsion when acting on a function capital F is this. And if you just channel through and you write, remember, dBF, now you can write it as pi b mu nabla mu F. You do all that computations. Ask me if you want. I can do it later offline. Offline. If you do all this computation, you just find out that this is equal to 0 if and only if the n wedge n is 0, which is great because that was our Frobenius condition. So if that is an hypersurface, then torsion must be 0. So the preferred D is torsionless. That is the first very important thing. And by what we just did, you already know that it must be, therefore, non-metric. Because if it is also metric, then the Lie derivative along L of Q is 0. And I don't want to impose that. I want the more general one. We're going to find that, actually. The second condition is now you can study how it acts on L, for instance, just by saying, but this is this. I know what this is. Well, you channel it through. It's a long computation. I spare you the details. What you're going to find is that this is not 0 is equal to theta AB, the same theta we had before, plus omega A LB, where now omega A is defined, and its definition is pi A mu, nabla mu L mu, Q mu B. Sorry, there's no Q, K. That's what I mean. Okay? Now this, you can furthermore split it into something orthogonal to L and proportional to L, such that LA pi A 0. This is sometimes called in the literature the Agi-check connection, and this is the inaffinity. The inaffinity, because that's really the bulk, L mu nabla mu L nu is equal to kappa L nu. That's how this kappa enters here. So L, B is not parallel transported with the preferred Carrollian connection. Good. Similarly, you can do the AKB. Again, long and tedious computation. Spare you the details, but the final answer is important. The same omega A that appeared there and the same pi that appear here. Plus, you remember the var phi? The var phi was the guy that was in dk equal minus k wedge var phi plus var pi. This var phi enters now. This is the way it acts on k. I have defined already everything and except this theta bar. Let me give you the definition. The theta bar is q mu, nabla mu, k nu, q, b nu, where that is defined this way. Now, theta bar b and pi, these guys, you can just show explicitly, ask me later offline if you want, that these guys, they don't depend only on L, K, and Q on the surface. They also depend on some bulk data that is not captured by L, K, and Q. This is true only by the symmetric part of theta. Theta is also an anti-symmetric part, but that is just capturing, because this is the anti-symmetric exterior derivative, it's just capturing this. So the anti-symmetric part is completely determined by the surface. Once I know K, I know var pi, but the symmetric part is not. And finally, you can compute how dA act on Q. It's the same computation. You project pi, 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 you channel it through, and the final result is minus theta AB KC minus theta AC KB. So it is not metric. Of course, it's not metric compatible. And what is this equation that seems that complicated? It's exactly what we found before. Before we found n minus 2n plus 2t was equal to Lie derivative of q. Remember? T is 0 now. N is exactly the tensor dAQBC. And LLQ is exactly theta AB. So that's what we found. We found that the induced connection must be compatible with the non-Levi-Civita discussion we did before. And it beautifully is as a computation. Okay, so end of the story here for the connection. The preferred dA is torsionless, non-metric compatible. It depends on theta B, phi A, and this anti-symmetric part of AB, which are intrinsic. This is just saying that the Christoffel depends on derivatives of the metric. There is nothing there. It's just it depends on KLQ. And then it depends on theta bar symmetrize AB and this omega A, which are extrinsic. We saw it in derivative, the failure of the Levi-Civita theorem, that you don't have enough intrinsic information to solve uniquely the connection symbol as a function of the geometric data. And so it's very natural that once you embed this in the bulk, it will depend by something that does not depend on KLQ. It depends by the bulk ambient space. Okay? Okay, I went a bit fast on this part. I hope that's okay. The final thing I want to write down. Do you mind if I take 5-10 minutes more? I know it's really long. Sorry about that.
No, you can go.
You want a break?
Me? No. In 10 minutes, I can finish. I mean, unless you want some details of this part. Of course, I went a bit fast, but I wanted to give you the main upshot, and then you can find the details in the review if you want. I think I want to really to tell you about the Einstein equations, because I think this is the most interesting part now, where you can see all this technical formalism really becoming very physical and interesting. So I want to cover that, if that's okay with you.
Okay, you can go for 10 minutes.
Okay, fantastic. So for doing that, I need to talk about three equations. The first one is called the Gauss equation. The second is called the Codazzi-Mainardi. And the third is called the Null-Brown-York stress tensor. So first, let me remind you the Gauss equation. Gauss equation is a way to determine Riemann on a surface as a function of bulk Riemann and extrinsic curvatures. I'm writing it like this, like if it's a sort of big equation, then I write it explicitly. That's the content of the famous Gauss equation. How do you do that? The way to do this is the following. On the surface, we know that R A, B, C, D, the Riemann tensor, when acting on a vector VB, is by definition, remember we defined it before in full generality, DCDD VA. We know this. But now we know how D is related to the bulk Levi-Civita, right? We know the famous D equal pi nabla. So we just go through, we replace every time D acts on the vector with pi nabla. We're gonna have an equation that contains at a certain point some projectors acting on nabla times the lift of the vector. That will pick up the bulk Riemann tensor, and then we just collect everything else. This is the content of this equation. So again, details can be found in the lecture notes, or you can just ask me later offline. If you channel this through, the final answer is pi AA. It's going to be a term which, of course, that's otherwise this is not the Gauss equation, contains pi r alpha, beta, gamma, delta times. Okay, so the way I'm writing it here, I'm sorry. Let me put this down. So, of course, by construction, what will happen is that when you then pull up the bulk Riemann, you're gonna get something that is again linear on V. So you then it's true for any V, and so you remove the V. So that's the statement that you find in the literature. RABC is equal to pi R plus what remains? It remains 2 theta BC K D, anti-symmetrizing the CD indices, of course, it comes from the commutator, times phi A plus phi A, minus 2 theta BC theta bar dA. This is the Gauss equation on the null hypersurface. Okay? Now, why it's interesting for us? Because suppose now you contract with LB. I contract all of this with LB. Remember, LB theta BC, we showed it 2 hours ago with all the gory details, is 0. So if you contract with LB, this term drops and this term drops. And then you get something that is very simple. You get LB R A B C D is equal to pi, spare me the indices, R alpha, beta, gamma, delta times L. There was an LB pi B beta. This is just the bulk lift L beta. So I'm going to remove 1 pi. Okay, that's what you get. But now, what is this? Well, this is very simple. It's DC, DD, LA. And now DALB, we know what it is. It's this theta AB plus omega ALB that I just computed before. And so we can use that information. And actually, I'm going to rewrite it in yet a different way just to make the notation pleasant for you. I'm going to introduce a tensor, which is a famous tensor called the Weingartner tensor, which is very simple for us. It's just DALB definition. which is, you remember, it was this theta AB plus omega A LB we just defined above. Okay? And so if you just put all of this together, what you found is that dc omega WDA minus DD WCA is equal to I alpha A, I B, no B, gamma C, I'm sorry, it's the opposite, pi C gamma, and pi D delta of R alpha, beta, gamma, delta, L, beta. This is a very important equation for us, and I'm almost there, I promise. Really, 3 minutes. Take the trace. Take C equal to A, trace. Here we have dC WDC minus DD WCC. Okay? Yes, is this clear? Equal pi alpha A, pi C gamma, pi D delta, and I'm sorry, I just promised I was going to take A equal to C, so I'm going to put a C here, R alpha, beta, gamma, delta, L beta. What is this? It's a projector. Pi is equal to pi. So this is pi alpha gamma. Okay? But now what is pi alpha gamma? Remember the completeness equation we just had. We show together that this was equal to this minus n alpha. Well, actually, this is not even the completeness. This is just the definition of it as a projector. And so let me plug it in. This is equal to, there is a term which is just pi delta delta R alpha beta alpha delta L beta. This is the term in which it sticks in the delta function. And then there is another term which is minus n alpha, K gamma, pi D delta, R alpha beta gamma delta L beta. Now remember, L A was defined to be pi mu A of n mu, right? But therefore, as I go into the bulk, I can replace L mu by n mu. So I'm going to do that here. So I'm going to call this n. And then I'm in the bulk. There's no problem with inverting anything. I can bring this alpha down, and I can bring this alpha up. So I'm going to get n alpha, R alpha. And this is 0 because of the anti-symmetry of the Riemann. The symmetric alpha beta in the first two indices down of the Riemann. This is the bulk Levicita Riemann. There's no doubt. We know that that's 0, so it's contracted with twice the same vector. So this, ciao, ciao, it goes, right? And this, we remain with the R alpha alpha contracted. That is the Ricci tensor. So final result, dCW dC minus DDW, I'm going to call the trace guy W here, it is equal to pi D delta R beta delta L beta. Okay, and yet another final step. I'm going to introduce TDC. Definition, WDC minus delta DC times the trace, right? So this object becomes the covariant derivative of this. I remember for you that this is very simple. It's not something weird. We know all these properties, dA, LA, right? So this is fully intrinsic plus the connection. So we know all of that. And now I wrote D, C, T, D, C, or let me even change the indices to make it even more appealing. D, B, T, A, B, it is equal to pi A delta R delta beta, this is symmetric, L beta. I'm almost there. I need to convince you that pi A delta G delta beta, LB, so I'm going to introduce the Einstein tensor. The Einstein tensor is R delta beta minus 1/2 G delta beta times R. I mean the bulk, so this is just a bulk Einstein tensor times LB beta. For the same reason as above, I can replace this L by N. I'm in the bulk now. These two things can be chosen to coincide on the surface when I'm near the surface. I use that this is just, remember the, I'm almost there. You have just to remember the, oh no, I use nothing. I just go through. This is pi A delta, R delta beta, N beta. Remember, N and L are the same. Minus 1/2. Now what do I have? I have R times pi A delta. Oh, I'm sorry, I was okay with sticking in the L here. Okay. Now L beta G delta beta. I'm in the bulk. So this guy is fully invertible. It's just equal to, or N beta, it's just equal to N delta. Down. But now what is N delta pi A delta? 0. By construction, this thing is orthogonal. So I prove that this is equal to this. And so I just stick it in the equation I wrote before. And this is pi A delta. By the way, what I derived en passant was the Codazzi-Mainardi equation. And finally, I introduced this T, and this as a name is called the Null Brown-York stress tensor. And it is called that way because I have just shown that its conservation law are the Einstein equations in the bulk. And this is the main punchline. All this very technical formalism, a bit overwhelming perhaps, and apologies about that, led to rewriting the Einstein equation on a null hypersurface as conservation laws for a stress tensor. So Gauss equation, Codazzi-Mainardi equation, the Codazzi-Mainardi equation, just if you like the nomenclature and relating, it was this quantity. This is called the Codazzi-Mainardi equation. And null Brown-York stress tensor led me to employ all the power of the Carrollian preferred connection that I had and the formalism to find that Einstein equations are conservation laws. Applications of these are infinite. We're thinking about flat space celestial holography, Carrollian holography, etc. We're thinking about fluid dynamics for this conservation law of these fluids, quantization of these conservation laws, because now we have conserved quantities and currents, and all of that. And I have to thank you very much and apologize for taking so much of your time, but I hope it was useful. Okay, I'm going to stop here. Thanks a lot.